And we're going to start recording. How is everybody tonight?
Hanging in there.
Good to hear. So, welcome to the last week of concrete design. And we are going to pick this up right from the lecture that we were working on last time. But before we jump right back into the example number 5 that we were working on before we do that, I wanted to talk a little bit about a homework problem because I graded the homework over the weekend and I saw quite a bit of confusion over this particular problem. As you can, hopefully everybody can see it on the screen. Hopefully anybody can see it.
Yes.
Thank you. Okay. So the homework problem was to define one point. We've been doing these column interaction diagrams by finding 5 points, and at each point we would find Pn and Mn, and then we would draw a diagram from those 5 points. The homework problem was to find just one of those 5 points, but this point was defined differently than any of the other 5 points, and I think this caused a lot of confusion. So this was the statement. This is the strain diagram as given in the problem, and this is defined as compression. So this means that the strain on the right-hand side of the column is 0.003 inch per inch in compression. The strain on the left-hand side of the column is 0.01 inch per inch in compression. So that means that every fiber of the whole column is in compression somewhere between 0.01 and 0.03. Okay, so that was the definition of the problem. Now, in order to solve this problem, you have to be able to calculate the strain at any given location on here. You need to know the strain in this row of steel and the strain in this row of steel. You also need to know what the condition of the concrete is. And in order to do that, you need to calculate what C is equal to. Okay? So little c, and I know this caused a lot of confusion for a lot of folks. That is why I want to cover this again real quick. C is defined as the distance from the extreme fiber in compression to the point where there is 0 strain. That's the definition of little c. Extreme compression fiber to the point of 0 strain. Well, the point of 0 strain does not occur within the column. There's no point inside the column that has 0 strain. All of the points in the column are between 0.01 and 0.03. So where is C? C, you have to extrapolate out to find where C is. And by extrapolating out, you find that little c, the dimension of, is from here to here. And that dimension calculates to be exactly 36 inches. Okay? Everybody on board so far?
Yep.
So,
Professor, how did you get the 36?
I took, how I did it was similar triangles. So what I did was I took 0.003 over C is equal to 0.001 over C minus, this was 24 inches.
Okay, cool.
Okay? Or there's a number of ways you can do it. You could do this triangle where 0.003 minus 0.001 over 24. There's any number of ways to formulate similar triangles to solve for C. But C, the point of 0, solves to be 36 inches. Now, what does this mean? What is the meaning of having a C that is outside of the face of the column? Can we have that? Absolutely. Yes, you can have C being outside of the face of the column. All you're doing is just extrapolating the strain diagram. So the point of theoretical strain is out here someplace. Even though you're not inside the column, that's okay. Because all little c does really is just sets up the relationship so that now I can calculate what the strain is at this face, at this steel, at this steel, and at this face. I know what the strain is at any given location on that column because I now have a definition of C. Okay? Is everybody all right with that so far?
Yes.
So now the question is, what and where is A, little a? Okay, so to find little a, I'm going to redraw my column here, right there, okay? And C is from here to here is little c. So where is A? Well, you still follow the rules, so to speak, in that little a is equal to beta 1 times little c. So that, in this case, equals 0.80 times 36 equals 28.8 inches. So little a calculates to be 28.8 inches in this particular problem. And so if I draw that, then that means my Whitney stress block, why are you not listening to me? Okay, see if this is green. There we go. Okay, that's my Whitney stress block. So from here to here is C, and from here to here is A. But this is where you have to look at the problem and say, well, wait a minute, A cannot be larger than the column itself. You can't have concrete and compression out here where there's no concrete, just by observation. You can't have concrete and compression if there is no concrete. So then that's where you need to discern that if A calculates to be bigger than the column, then A is going to be the size of the column. So that means that A is equal to 24 inches. And this rebar is inside of A. This rebar is inside of A. So C sub C, the compression in the concrete, is equal to 0.85 F prime C, the width of the column, 24 inches long, minus both areas of steel, because both areas of steel exist inside of A. Okay? I think this was the real confusion. What do you do if C is outside the face of the column? And a lot of students got confused in different places, and I just want to make sure everybody's on the same page here. This is the, C is 36 as defined by this strain diagram. You can't change that. You can't go to, well, C is measured from this steel to the over here. That's not, you can't say C is bigger than the width of the column, so C is equal to the width of the column. That's not valid either. C is 36 inches. A is the one that you have to modify because the compression can't be outside of the column face. And lastly, there were a number of you who calculated all this perfectly right, got this right, found that the force in the steel here was something like 72 kips or 72.4 kips, something like that, but failed to recognize that this is in compression. Because C is outside of here, nothing inside the column is in tension at all. So you got so close, but you subtracted this force instead of adding this force because this is in compression, not tension. Okay, so I just wanted to touch on that real quick. Do I have any questions on that problem?
Professor, on the solution manual, at 24, you call a strain of 0.002, but isn't it 0.001 here at 24?
To calculate C, what was I doing with the 002?
You were calculating, yeah, I think you were, calculating C.
Okay, then what I was doing, and thank you for the question. What I was doing, let me grab another color here. I was using this as my triangle. That's a horrible drawing, but okay. That's every time I try to make it better, I can make it worse. Let's just get rid of it. Let me try this. Okay, so I went from here to here to here to there. That's better. That was my triangle. So 003 minus 001, the height of my triangle was 002. The width of my triangle is 24. That was my triangle that I used to establish similar triangles.
Okay. Thank you. Yeah, I was just a little confused about the 0.002.
Okay. Any other questions on this? This is actually a pretty important topic because in concrete design, up until now, and I realize how, I mean, it's totally makes sense why everybody would be confused, but up until now, we have had strain diagrams that look like this, where C was measured from 0 to the compression, and this steel over here in the bottom of the beam was in tension. This is what we've done up until now. But columns are not constrained by having tension and compression. They very well could have all compression. And C could be outside of the face.
Professor, when you calced E sub S and E prime sub S,
Yes.
you used 15 and 33 for the length.
Yes.
I have to go back and review it, but do you remember were those the lengths to the reinforced steel?
The 15 is from 0 to here.
Okay.
And you said 33?
Yeah,
That's from here to here.
got it.
So again, using similar triangles.
You were able to get those values.
Right, because this is 36. And then, so 36 is the big triangle. And then you find the little triangles and you solve for the unknown is the strain. Yeah, so again, it's just similar triangles.
All right, thank you.
Okay. Anybody else? Any other questions on this? All right. Then where we left off last time was the design of a footing. And we were working our way through example 5. I will backpedal a little bit so that nobody's completely lost of where we were. Okay, so backpedaling just a little bit. What we had was a square footing with a rectangular column. The footing is defined as square, so B is equal to D. And we had a load given of 875 dead, 220 kips live. The concrete is 4,000 PSI. Rebar 60 KSI. Concrete density is 150. The allowable soil pressure is 3,500 PSF. And our job is to design the thickness of the footing to resist shear and the size of the footing so that the soil pressure is allowable and the flexural steel for the given loading. So We have to check bearing pressure. We have to check one-way shear. Excuse me. My voice is just already going out. That's a bad sign. We have to check one-way shear. We have to check two-way shear or punching shear, and we have to design the steel. So we started with what is going to end up being a rather ridiculous initial guess, but we started with H equal to 14 inches. Then what we said is the bearing pressure is equal to the total load over BD plus the weight of the footing itself. So P is 875 plus 220. That is not factored because we're starting with checking the soil pressure. P is 1095. We solve for the required B. Q is equal to P over BD plus the weight of the footing, less than 3,500 PSF. So 3,500 PSF is 1095 over B squared plus the 150 times my initial guess of 14 inches. And I solve for 18.15 feet. So I'm going to try, or I'm going to start with an 18.5 foot wide square footing. Then we have to calculate our shear demand, VU. And I'm going a little fast because I'm catching up to where we were last time. So VU in one-way shear is based on this idea here. If this thing is going to fail, then it's going to fail along this diagonal crack here, going through the width of the footing. So if I drew a free body diagram, then this portion of the footing is trying to be pushed up while the rest of the footing is being shoved down. So the only pressure that we actually care about is the pressure on the piece here that's being shoved up, which is just this area right there. So PU is either 1.4 times 875, 1225, or 1.2 times 875 plus 1.6 times 220, or 1402 kips. The 1402 is greater than 1225, that controls. So now my QU is 1402 over 18.5 squared is 4.096 KSF. Now, before we get too far into this, remember that the 18.5 was based off of allowable soil pressure. The allowable soil pressure was in a small part, but partially based off of the thickness of the footing that we had assumed, which was 14 inches. If this footing ends up being significantly thicker, then it will be heavier. If it is heavier, then the bearing pressure goes up, and this 18.5 may no longer be valid. So as we iterate through this solution, always keep in mind you have to back check your bearing pressure if your footing gets thicker. D is equal to H minus 4.5. So my D is only 9.5 inches. My VU, now we need D to calculate VU because VU is defined as the distance D from the face of the column. So I'm going to find the area of this surface area down here on the footing. The area is the width of the footing times this length right here times my factored bearing pressure. So the width of the footing is 18.5 feet. The bearing pressure is 4.096 KSF, we just calculated. But this length right here is going to be the length to the halfway point is 18.5 over 2 minus half the width of the column, which is 18 over 2, minus D, which is 9.5 inches. That's how I get to this length here. And so VU is 584.2 kips. VVC is phi times 2 times lambda square root of F prime C BD. As we said before, normal weight concrete almost universally is used for footing, so lambda is going to be equal to 1. B is 0.75, 4,000 PSI concrete. I got a B of 18.5 feet times 12 inches per foot times D of 9.5 inches, and I get 200.1 kips. 200.1 is less than VU, therefore my footing solution so far is no good. So let's go back and try something thicker. Let's try 30 inches, since 14 wasn't even close. Okay, so at 30 inches, I have to reanalyze whether or not my footing size is still okay, because my footing itself got heavier. So I'm going back to that step before where we sized B, because now I've got 150 pounds a cubic foot times 30 instead of 14. So I solve for B, and instead of minus, I forgot what it was, but it was like 160 something, now it's minus 375. So the footing got significantly heavier. So B now has to be 18.72. 18.5 doesn't work anymore. So now we choose B to be 19 feet wide. So don't forget this step. If you thicken the footing, you have to reanalyze the size of the footing. So QU is now 1402 over 19 squared, which is 3.884. So it went from 4.96 to 3.884. D is H minus 4.5, which is now 30 minus 4.5, 25.5 inches. So now VU is my new QU times my new B times this distance here is 19 over 2 minus 18 inches over 2 minus D is 25.5 inches. And I get 488.9. So isn't this interesting? Just by making the footing thicker, my VU has gone from 584 to 489. That's the actual demand went down. And VVC, as I said a moment ago, but now I got 19 and 25.5, and 551.6 kips is greater than VU of 488.9. So now my proposed thickness is acceptable at 30 inches. Okay, so this is where we left off last time. And I have a question that says, when do you use D equals H minus 4.5 versus D equals H minus 3.5? Great question. And I actually got that question during office hours. So for those that I answered it for, forgive me, I have to do it again. The answer to the question is, if I have a strip footing where my flexural steel is running left to right and going in and out of the page is only my minimum steel for temperature and shrinkage. Okay, so in other words, my in and out of the page, this footing could be 10 feet long or 15 miles long, doesn't matter. This is a continuous strip of footing in and out of the page. So only the steel on the bottom is actually working and bending. The steel on the top row is just there for temperature and shrinkage. When you have this situation, this is a strip footing, then the only steel that's actually working in flexure is the bottom. Then you can say D is H minus 3.5. Conversely, if this is a square footing, and so the steel on the bottom is working in bending, and the steel on top is working in bending as well. They're both working in bending, it's just one's going east-west and one's going north-south. Then you don't know which steel is going to end up going which way. You can't control that. So you have to assume the most conservative case for your steel. The load is basically the same in both directions because it's square. So now you have to assume that this steel is your controlling case, You design for D equal to H minus 4.5, and whatever steel you get, you just put it in both directions, and that way you're covered. To my private questionnaire, did that answer your question? Okay,
Professor, can I ask a question?
of course.
The QU is your bearing pressure. That's correct, right? From the footing
Yes.
exerted.
Yes, your QU is your factored bearing pressure.
And that's the pressure we calculated that's going to be exerting onto the soil below, or does that make sense?
Well, it's the pressure that the footing is exerting onto the soil below. It is also the pressure that the soil is exerting on the underside of the concrete. The whole action equal and opposite reaction deal.
And the QA in the beginning is from the geotech report, like
That's correct.
how much the soil can handle.
Yes.
Do you compare QA ever with QU?
Never.
Oh, okay.
Never, ever, ever, ever. And thank you for asking that. I want to make sure that's clear for everybody. The QA is to be compared with service level loads. The QU isn't really so concerned about what the soil's going to do. It's concerned about what the soil's going to do to the concrete. So it doesn't even really matter if the soil could ever actually hold the QU. If QU is 3884 pounds per square foot, it doesn't even really matter if the soil can even take 38.84 pounds per square foot. It's that if it did support that much load, it would exert that much pressure on the concrete, and we want to make sure the concrete doesn't fail.
Okay. Yeah, I was getting a little confused because I was comparing QA with QU and thinking, how is it going to support the footing if QU is greater? But
Right.
that's because it was factored.
That's because it's factored. Yes.
Yeah. Okay.
And QA is proportionate to service loading. So QA does not by any means mean that anything above that value in the soil just turns into liquefaction steam and the whole thing just drops to the center of the earth. That's not what's going to happen at all. What happens if you have service level loads greater than QA, then you have several failure modes that could happen. One of them is just that the whole thing squishes too much and you have an unacceptable amount of deflection. So this whole footing, concrete and all, might drop too much. And it's just an unacceptable value. So you have to keep the soil pressure low enough to keep the overall deflection within an acceptable value. Everything's going to compress the soil to some degree, right? Even if you're walking in the grass, you're actually compressing the soil to some degree, but certainly not enough to even notice. So the main failure mode that you have to keep Q under QA is deformation. But there are other modes where if the bearing pressure is too high, you have these failure modes where the soil kind of shears along and this whole thing can kind of topple over. And if you take soil mechanic classes, they talk more in detail about shearing and deformation and other failure modes of those. But when they tell you QA is equal to, what did we say in this case, 3,500? Yeah, 3,500. There's a huge safety factor already built into 3,500. It may not actually do anything super scary until you reach 5,000. But they're not going to tell you 5,000. They're going to tell you 3,500 because that is proportioned to your service loads.
Thank you for clarifying that.
Okay, great. All right, so is everybody warm and fuzzy now? Can we move ahead? This is pretty much where we left off last time.
Yes.
Okay, I got one yes and no no's.
Yep.
I
We
got
could
two
go.
yeses and no no's. Okay.
We're good.
I just had a quick question. So the QA is literally only used to find the dimensions of the footing, technically.
No, not exactly. We're using it to find how big does the footing need to be in order for the soil pressure to be under the allowable, but it's really an allowable. So there might be other situations where things are more complicated, and what you would want to do is calculate what the service load bearing pressure is, and you always keep that under the allowable. There may be other situations where the size is dictated by something else, but you still want to make sure that the actual pressure is less than the allowable pressure. That makes sense?
Yes, it makes sense. Thank you.
We're just using it to size the footing so that we are guaranteeing that is what's going to happen. But there are other situations where this size may be dictated by something else. The bottom line is whatever bearing pressure we are causing still needs to be less than the allowable. Okay, moving forward, what we have discovered is that a 30-inch thick footing works for one-way shear. 551.6 is greater than 488.9, so therefore we go to the next step. We've passed the first step. Okay, so the next step is we're going to try to use a 19-foot by 19-foot by 30-inch footing. Let us check punching shear and make sure that that is okay. So punching shear, here's my 19-foot by 19-foot footing, and my column was defined as 18 by 24. The failure surface for punching shear is along this dotted line. The dotted line is defined as from the face of column D over 2. D was 25.5 inches, so D over 2 is 12.75 inches. So we go from the face up 12.75, down 12.75, to the right 12 3/4, to the left 12 3/4. That defines the size of this failure surface box that we have here. Now, the equation for your capacity is the least of these three equations. We presented these last time. Whichever one of these three gives you the least capacity, that's the one to use. Where the beta is the ratio of the long to short side of the column, which in this case is 24 to 18. Beta is equal to 1.33. Alpha S is equal to 40 for an interior column. It would have been 30 for a side and 20 if it was on the corner. Beta naught is the perimeter of this failure surface. So beta naught is 2 times this length here. This length is 18 plus D over 2 plus D over 2. So 18 plus 2 times D over 2 plus 2 times this length is 24 plus D over 2 plus D over 2. Altogether, the perimeter from here to here to here, back to here is 186 inches. So now that I have F prime C, lambda is 1, beta naught, D is 25.5, I can plug those all into here, and I get a VC capacity of 1199.9 kips. VC could also be 2 plus 4 over beta. So 2 plus 4 over 1.33 is 1499.9. or VC could be 2 plus alpha S D over beta. So you got 40, 25.5 over 186, and that's equal to 2245. So clearly, equation A is the one that controls in this situation at 1199.9 kips. VVC is 0.75 times 1199.9 is 899.9 kips. Okay, but what is VU? What's my demand? Well, my demand is all of the QU bearing pressure that is not inside of this square. This square here is what's going to punch into the earth. Everything that's hatched is what remains. So it's the total force on the portion that would separate from the column that you have to design for. So VU is equal to my factored bearing pressure, 3.884 KSF, times the whole shebang is 19 squared, but you can take out what's in this inner square. And this inner square is 8, again, this is what I did before, 18 plus 2 times d over 2 times 24 plus 2 times d over 2 is, and then you convert it from feet squared, you convert it from inch squared to feet squared. All of that equals 1344.1 kips. Anybody see a problem here?
It's not being multiplied by 2 when you're subtracting, like above, or is it something else?
It's greater than VC.
VU is greater than VVC. Yes. No, this part here, you don't multiply times 2 because you're just taking this length times this length. The perimeter was 2 times this length plus 2 times this length. Of course, an area is just width times height.
Oh, just for the area. Yeah. Okay.
Yes. And then it gets a little confusing because these are all inches, and then you have to convert it to feet because 19 is feet squared and 3.884 is kips per square foot. So you got to keep all your units straight. But no, the problem is VU is a lot bigger than VVC. That's no bueno. That doesn't work. So what do? You just crumple it all up and throw it in the trash can and go for a walk, right?
Think you'll increase the height?
Increase H.
Or you could try increasing your thickness. So let's try, instead of 30 inches, let's try 36 inches, where D then becomes 36 minus 4.5 is 31.5. Beta naught, so I'm taking D over 2 is here and here. So beta naught is now 210. A is 4 times 4,000. Put in the 210, put in D. Now I got 1673. VVC, I already know that A is the controlling case, by the way. VVC is 0.75 times 16 is 1255. VU, now here's a good point. Do not automatically assume that this is still not working because VU was 1300 and something, because VU changes. As the footing gets deeper, the 36 inches, as the footing gets deeper, then that square gets bigger because the square is defined as D over 2 from the face of column. So as that square gets bigger, this term in here gets bigger, so VU gets smaller. Now VU is equal to 1345. Okay, well, it still doesn't work. But just remember that as the footing gets thicker, VU gets smaller. But it still doesn't work. All right, so let's try H equals 40. And I'm getting a little worried about my bearing pressure, so I'm going to check it. And now I need 19.11 feet because my footing has gotten so thick that it's taking, this weight is taking away from my allowable bearing pressure. So now we need to make the footing bigger, 19.3 now to cover the bearing pressure. QU is now 3.783. It got smaller because the footing got bigger. D is 40 minus 4.5 is 35.5. Beta naught, this is D over 2. D over 2 is now 226. VC is now 2029.7 kips. VVC is 1522.3. VU, now QU got smaller, the footing got bigger, and the hole in the middle got bigger as well. So basically everything in this equation changes. VU is now 1318, less than 1522. Okay, now we have passed that test. We need to recheck our one-way shear because we made the whole thing bigger. So 3.783 times 19.25 wide times an area of 19.25 over 2 minus the column minus D is 430.9. VVC is 778. We got this totally covered now. So therefore, we have now double-checked our bearing pressure. It still works, or now it works again at 19.25. We checked our one-way shear, and we checked two-way shear. So this is kind of how we honed in on the answer. But as we were honing in, see, you notice the thickness of the footing got deeper, and the size of the footing kept getting bigger until we came to a solution. Okay, so the shear design is completely satisfied now with a 19-foot, 3-inch square by 40-inch deep footing. Now we need to design the steel. Since the footing is square, flexural demand will be equal on both sides, so the side with the lesser D will control. We're going to use D equal to 35.5 inches. That's 40 minus the 4.5. Which side is going to control the flexural response when the column's not square? Well, it's going to be the side with the greatest hatched area. And because this is 24 and this is 18, then the one with the greatest hatched area is going to be the one on the face as shown. Does this make sense to everybody?
Yes.
If I draw a line here and hatch this, this is going to be smaller than this hatched area because this is 24, this is only 18. So this is my controlling side area where the flexural demand is going to be greatest. So MU is equal to QU, 3.783, times the width of 19.25 times this depth here, which is 19.25 to the center minus the 18 over 2 is the area times that distance again over 2 to get the moment arm, right? So the force is pressure times width times length times the moment arm of the length over 2. So this is squared over 2. Everybody get that, or did I lose anybody?
I'm lost.
Okay, okay. So, how do I, let's see. I don't want that. That was the wrong one. If I have a fixed support and I have a cantilever beam, right? Classic mechanics problem. So this is fixed cantilevered beam, and I apply a load to this cantilevered beam, and that load is of a magnitude WU, and my cantilevered beam is of a length L. Then what is the moment at the face here? And the moment at the face there, MU, is equal to WU times L times L over 2. right? Everybody remembers this or can see this?
Yes.
Okay. Okay. Well, if you remember or understand this, then that's what this is. That's all I'm doing. Except that WU is QU times the width. So QU times the width is equal to WU, kips per foot. And then L is this term times L over 2 is this term again over 2. So that's that. All this is this.
Professor, what's the L is 19.25 over 2?
19.25 over 2 minus half the column width.
Oh, okay. And then there's 2 of them, so you square it, and then it's over 2. Okay.
Yes, yes. But L to here, this is the column face. So you have to go 19.25 over 2 gets you to the center of the column minus half the width of the column to get to the column face, which is here. Okay, so everybody all right?
Yes.
So using this for MU, I get 28.68 kip feet. That's a big load. That's a really big load, but it's spread out over a width of 19'3". Yep, okay. All right, so now I have a moment and I have a section. This becomes an analysis problem for a singly reinforced rectangular beam. Rn is mu over phi BD squared, which is 2868 times 12 to get to kip inch over 0.9. B is 19'3" is 231 inches, and D we found to be 35.5, and then it's D squared. So Rn is 0.131 KSI or 131 PSI. Using the tables, I get a rho needed of 0.0023. So AS required is rho BD, 0.0023, 231, 35.5, 18.86 inches squared. Sounds like a lot of steel. Minimum temperature and shrinkage steel, though, is going to be 0.0018 times 231. Now remember, temperature and shrinkage is not times D, it's times H. It's the gross section. So that's going to be 16.63 inches squared. My flexural requirement is greater than my temperature and shrinkage requirement. So I'm going to go with flexural 18.86. And I'm going to choose a bar pattern. Now remember, this is really important. Just getting to this point here, you haven't designed the footing yet. You need to choose a bar pattern that is going to satisfy both the total steel needed and spacing requirements. So with 15 number 11 bars, AS is 15. There's a typo. Okay, sorry about that. This is supposed to be 15 number 10 bars. So let me make sure the number's right. 15. Yeah, okay. This is supposed to be number 10s. 15 number 10s is 19.05 inches squared, more than 18.86. And remember, always, always, always remember, go back and verify that phi mn is greater than mu, or phi vc is greater than vu, or phi pn is greater than pu. Whatever it is you're checking or designing, always go back and verify that you actually have what you think you have. So for a singly reinforced rectangular beam, I go back to our familiar equation. I plug in all the pertinent values, and I get 35,770 kip inch, or 2981 kip feet. Greater than 2868, So we are okay with my 15 number 10s. Then what I did, I didn't really outline it here, but I took the width of my footing is 19 foot 3. This came up during office hour, and it's a very good question. So what you do, this is a section through your footing, and you have these rebars now. I'm not going to draw all 15 of them, but you can assume the first one is 3 inches from the edge. The last one is 3 inches from the edge. And if I have 15 number 10s, that means I have 14 spaces. So if I did this right, I took 19.25 times 12, 231 inches wide, minus 6 inches, and divided by 14 spaces, and I get 16.07 inches on center. So I just tell them, put 15 number 10 bars at 16 inches on center. And because I use D as H minus 4.5, then I know it's going to work in both directions, because I actually designed the top row. The bottom row is going to work because it has an extra inch on the D. And so this would be my design, 15 number 10s at 16 inches on center.
Professor, if the area of steel was greater for the temperature and shrinkage, would you have used that area to design for your steel design?
Yes, you have to.
Okay.
Yes, you have to. And so say like that would have been bigger, then maybe I would have used 15 number 11 bars at 16 inches on center. But I still would run it through my phi-min equation just to be sure that my flexure capacity is greater than the demand. Even if I sized the steel due to temperature and shrinkage, I still want to make sure I didn't mess up someplace and grossly miscalculated something. This is your only way of knowing that you have actually satisfied the flexural demand. Does that make sense?
Yes.
Okay. Now we need to check our development length. Here's my footing again. Here's my 19 foot 3. Here's the width of my column. My critical section is right at the face of the column. So I only have this much length to develop number 10, or yeah, it was 10s. Is that right? Yeah, it was number 10s. Okay, the typo was 15 number 11. Anyway, I got 15 number 10s. I need to be sure that a number 10 bar has sufficient length to develop it, or else I don't have a number 10 at this critical section here if I don't fully develop it. So here's my equation. We talked about this 2 lectures ago, where lambda is 1 for normal weight concrete, psi t is 1 for bottom bars. Clearly they're at the bottom. Psi e is 1 for uncoated bars. Psi s is 1 for number 10 bars. And CB is the smaller of the half spacing, which is 16 over 2 equal 8, or center of the bar to the nearest face is 3.5 inches for the bottom row. So CB is equal to 3.5. KTR is equal to 0 because I have no shear steel in this thing. And DB is 1.27 for a number 10 bar. So I plug in all the pertinent values again, but we can't take this value to be greater than 2.5. So I did a quick check. It was more than 2.5, so I plug in 2.5, and I get 36.1 inches is my demand. What I have available is half of the footing minus half of the column minus the 3-inch spacing at the edge here, and I have 100.5 inches, way more than 36, no worries. So here's my final design sketch. The footing is 19 foot 3 square. It's 40 inches deep. I have 3 inches of cover to the bottom row, and I have 15 number 10s. EW stands for each way. So 15 number 10s left and right, and 15 number 10s in and out of the page. 0.75, where did you see 0.75?
In the LD equation, Professor.
0.75? Give me a hint.
3 lines above from the bottom.
1, 2, 3.
Right there.
Point.
0.75. Yeah.
Ow!
It was supposed to be 1.25.
Yes. Oh, that burns you. You guys ever end up teaching sometime in your career, you will know my pain. These typos drive you nuts. Yes. Thank you, Brandon. That is supposed to be 1.27. And that probably messes up the whole thing. Nope, it's still 2.76. So 2.76 is larger than 2.5. So 2.5 would end up being in there. But you're right, that should have been 1.27.
Professor,
Yes.
why did you assume 3.5 instead of half, 3 plus half of the diameter of number 10s for the CB?
Yeah. As you refine the design, you could get this more closer to it, where it would be 3 plus 1.27 over 2 would be 3.64. You are correct. But that's only if you wanted to like really, if this makes any difference, then you might refine that. But 3.64 over 1.27 is still greater than 2.5. So it doesn't really make any difference because that's going to be 2.5 anyway.
Makes sense. I thought it was always half. That's why.
Professor, would you mind
Yes.
saying how you got the 16-inch again for the spacing?
Okay. 19 foot 3 is 201 inches. 19.25.
Isn't it 231?
231. Okay, so 231 is the width. Let me go to my final design sketch. Okay, see all the dots right there?
Yeah.
Okay, so 231 inches minus 3
For the
is,
cover?
for the cover, is 225 inches from bar to bar. If you have
Okay.
15 bars, you have 14 spaces. So 225 divided by 14 is 16.07 inches. And I just rounded down to 16.
Okay. And in the drawing, you don't have to report the 16?
You do not. And that's a great question. If I have a square footing, typically a square footing, they're not going to go by a spacing because it's a hole in the ground. They literally dig a hole in the ground. So what they're going to do is count out 15 number 10s and throw them in the hole and then just spread them out until they're all nice and even. But on a strip footing is not a finite hole in the ground. It's a elongated trench. So it's not convenient to tell them, all right, everybody, for this side of the building, I need 214 number 6s. But over here on this side, I need 483 number 6s. They're not going to appreciate that. So if it is a strip footing with, and you're going to use the same design for the strip footing, whether it's on the short side or the long side or in the middle, then spacing is more appropriate. Just give me number 6s at 12 inches on center, and they'll figure that out. But for a spread footing, for this type of problem, they're going to dig a hole, count out the bars, and throw them in the hole. Do you see the difference?
Yeah.
So for spread footings, we don't give them a spacing, we give them a finite number. In this hole, throw 15 of them going this way and another 15 of them going the other way. And they'll spread them out. You just need to check the spacing only for the purposes that you can't have a spacing greater than 18 inches. That's really the only reason you're checking the spacing. Other than that, they're going to build it by just throwing that number into the hole.
And is there temperature and shrinkage there too, but we're just not showing it?
No, there's not.
Oh, okay.
No,
Oh, the
there's-
flexural still is the taking the place.
Yes, thank you for asking that. I want to be very clear about that. You do not have the steel that I showed plus temperature and shrinkage. Temperature and shrinkage is the same steel. It's just which requirement is larger, the requirement for flexure or the requirement for temperature and shrinkage. Whichever of the two is the larger value, that's what you size your steel for, but it's the same steel. In other words, you're not going to put 15 number 10s in here and then put in number 5s at 8 inches on center for temperature and shrinkage. No, it's the same steel. It's just whichever requirement is larger.
And you said EW is equal width? Sorry, I missed that.
EW is each way.
Oh, each way. Okay.
Each way.
Thank you.
Okay, let's finish up this lecture. Only got 10 more slides or so, and then we'll take a break, and then we'll start today's lecture. So let's wrap this one up. If you have rectangular footings are designed very much like square footings, except the flexural reinforcement in the long direction will control, so should be placed on the bottom layer. ACI 318 section 13333 states that a percentage, gamma S, of the flexural steel on the short side must be placed in a band equal in length to the short side dimension. I'll give you an illustration here. But gamma S is equal to 2 over beta plus 1, where beta is the ratio of the long side to the short side of the footing. So in other words, if you have a rectangular shaped footing, then the bottom layer of steel is going to be your steel going left to right, because the moment on this ear is much larger than the moment on the short side here. So these bars going left to right are going to be more important than the bars going up and down. But what the code is saying is that when this thing is bending on up and down, it's not going to be so even, because this is so disproportionate. You're going to have more stress here than here or here. So we have this equation here that says a percentage of the flexural steel on the short side, you can't spread it out evenly. And let me draw something here. We're talking about the steel going this way. That steel cannot be spread out evenly over the whole length here. You have to have more of it by this ratio in here, where the stresses are going to be higher. And then you have less of it out here because the stresses are lower. So I'm trying to illustrate the spacing's tighter inside of here than outside of here. In the other direction, this way, you just design it the same as a square footing. You just make sure that this steel is on the bottom row, because you're going to need it. The moments are much higher for this steel than for the shorties. Okay, did that make sense?
Yeah.
And the balance of the short side reinforcement is evenly distributed in the end regions. So that's it for this lecture. But I want to make sure, is this clear for everybody? How you design is just a slight modification than how we did the square footing. Okay, not hearing any questions, so let us reconvene here at 6:15.
Sounds
Perfect.
good.
Okay. We are back and ready to start today's lecture. Today's lecture is going to be about retaining walls. And retaining walls are kind of a specialized wall footing system that is there to resist horizontal or lateral soil loads. So retaining walls actually can be made out of many different materials. We can use concrete block, we can use concrete, we can use retaining walls made out of soldier piles, steel piles with lagging wood or concrete in between them. But today what we're talking about are really cantilevered retaining walls where we have a footing and we have a concrete wall that is cantilevered off of that footing to resist soil loads. Like so. So here's some of our definitions here. This is my footing. This is my retaining wall. We call it a stem wall. The outside face this is the toe. This is the heel. This is our retained soil that is providing the pressure. And this is our base soil that's providing some resistance. In addition to the structural design of concrete wall and footing, retaining walls are governed by Chapter 18 of the current building code, International Building Code, or we use the California Building Code here. And the governing conditions of the building code are for overturning, sliding, and allowable soil pressure. A typical procedure is to consider a 12-inch wide strip of wall and resolve all the forces on that section to check overturning, sliding, soil pressure, and then to design the concrete portions to the prescriptions of the ACI 318 code. So in other words, we're going to proportion the size of the footing and the wall itself to make sure that nowhere on this wall is the soil pressure greater than our allowable. But we're also going to make sure that it is not prone to overturn or slide. So those are all serviceability checks that we're going to do. And then once we're confident that we have our size correctly, then we're going to factor the loads and actually design the concrete itself. Several soil parameters must be determined and are typically investigated and reported on the project soil report. As a minimum, a soil's unit weight, gamma, the lateral active earth pressure, Ca times gamma, or an equivalent fluid pressure, gamma EF, coefficient of friction, mu, and allowable soil pressure, Qa, must be known to design the retaining wall. Like a spread footing design, service level loads are used for the soil portion of the problem, overturning, sliding, and soil pressure, and factor loads are used for the concrete strength designs. Active soil pressure. Just out of curiosity, have you guys had this before? Is this new or is this a refresher on soil?
Pretty new to me.
Okay, so terms like active soil pressure, passive soil pressure, is this new for you?
I heard it in 4400.
I'm sorry, you heard it on 4400?
C 4400 retaining walls. Foundation and retaining walls.
You guys have had a whole class on retaining walls?
Foundation and retaining wall.
Foundation retaining walls.
All of us.
Not me.
Okay. All right. Well, for some of you, then this is new, and I guess for some of you, this is review, but it's only one lecture, so forgive me. It's a review for you. Okay, but active soil pressure. Active soil pressure is the lateral pressure from gravity pulling down on the weight of soil. The magnitude of the lateral pressure is a fraction, C sub A, of the density of the soil, gamma, and is dependent on the soil parameters like internal oh gosh, what was that? I totally spaced on it. Internal coefficient of friction and other factors that, again, are determined by the soils report will determine how much lateral pressure you get from gravity pulling down on the earth. So if this is my wall and this is my soil being retained, an unsupported cut of soil will tend to slough or to press in like so. And the pressure is highest at the bottom where you have the most gravity pulling down on the weight, and it's least at the top to slump as shown. Okay, so if a soil is contained by a wall, it will develop an active soil pressure that is similar to retaining fluid, like water behind a dam. It's not water behind the dam, but it kind of acts like it. And in the sense that the farther down you go, the more weight you have pressing down on this, the more horizontal pressure you're going to have on that wall. And so your lateral pressure profile is going to look like this from this wall retaining this dirt. Because the pressure from the active soil pressure and from retained water are so similar, because basically water behind the dam has exactly the same profile, many times the active soil pressure is defined as an equivalent fluid pressure, gamma EF. When given in this form, then the lateral pressure at any height from the top of the wall can be found by multiplying the equivalent pressure by the height, like you would do for any kind of a fluid behind a dam. So if I go down from the top some distance h of x, I know it's kind of hard to read, but just a random distance h of x from the top, you want the pressure p sub x at that point, then it is just gamma EF times h of x is what equals that pressure p sub x, where p sub x is the pressure at some arbitrary point down from the top of the wall. Any questions so far? Okay, so active soil pressure, the active pressure at the base of the wall, P sub A, is equal to the equivalent fluid pressure, gamma EF, times the total wall height, H. The total lateral force on the wall, H sub A, is equal to the sum of the active soil pressure along the whole height of the wall. Okay, so what I'm saying with an illustration is the pressure at the base of the wall, P sub A, is equal to this gamma EF times H. H sub A then is the area of the whole stress diagram. You sum it, and I've got it shown at 1/3 of the height of the wall up because this is a triangle. So H of A is equal to the area of the triangle, and it's located at 1/3 up from the base of the triangle. So again, I just said with words exactly what I'm going to show you. So H of A is equal to half, because it's a triangle, P sub A times H, which is equal to half times gamma EF H squared, because P sub A is gamma EF times H, so half of gamma EF H squared. H of A is located at 1/3 of the wall height up from the top of the footing, or 2/3 of the wall height down from the top of the wall. Passive soil pressure. Passive soil pressure, as opposed to active, is the soil pressure is the resistance of the soil to movement. So if I had all this soil here and gravity is trying to pull it down, so it's pressing to the left, if I had some soil here up against this footing, in order for the whole wall and footing to slide to the left, it would have to push the soil out of the way. and there's some resistance to that. Passive soil pressure is the resistance of soil to being shoved around, but passive soil pressure is much less than the active soil pressure that is causing it. For a retaining wall design, the passive pressure helps to resist the active soil pressure trying to move the wall. Passive soil pressure is also defined by the project soil report, but for retaining walls, generally it is conservatively ignored, and for several reasons. No, I didn't go into the reasons. Okay, so a lot of times you kind of ignore this. For one, it's not really a lot. Two, you can't be sure that in the future this won't be dug out or eroded away. And three, it's kind of hard to dig this footing here and pour the concrete up against the soil without disturbing the soil. The passive soil pressure has to be from undisturbed soil. So you would either have to have a soil that you can dig out and it holds its shape, kind of like a clay. It can't be really sandy or silty because it'll just fall into the hole. Or you would have to, if it did fall into the hole and you got to cut it back, you'd have to pour this footing and then you'd have to compact the soil back in here, like an engineered fill. And it's just not really worth it. So most of the time for something like this, you would ignore the passive soil pressure. Sliding resistance. Let me go back to this image here. So if I don't count on this, then what do you have that prevents this whole assembly, the footing and the wall itself? What do you have that keeps it from just sliding out of the way and allowing the soil to slump down? Your main resistance to sliding is, sliding friction. Total active soil pressure lateral force, H of A, is generally resisted by your sliding friction, R sub S. And sliding friction is just that. It's the concrete poured up against to and sitting on the soil provides a frictional resistance here that resists the lateral movement. This resistance, R sub S, is equal to the weight of the wall, the footing, and any soil bearing on top of the wall times the coefficient of friction, mu. So that's the weight of the footing, the weight of the wall, and the weight of all the soil on top of the footing that is pushing down on this, that is providing a resistance to this sliding. Building Code section 1806.1 specifies that the factor of safety for sliding must be 1.5 when using service loads for the check. ASCE 7 section 2.4.1 specifies that D, L, and H loads all have a factor of 1.0. So when you do this check, the dead load is 100%. If you have any live load up here, you use 100%, and the H force load is 100%. Everything's a factor of 1. If the sliding resistance from friction is inadequate to resist the applied lateral load, then you can form a key. A key can be built into the underside of the footing. So when they dig this out, they would dig out this shape here, and then when they pour the concrete in, it would fill in and form a key. Oh, again, I didn't go any farther than that. But what this key does is it creates passive soil pressure right up here against this. And this passive soil pressure is confined by the weight of the concrete above it. So this does give you some real resistance if the friction alone doesn't do it. Have any questions so far?
Nope.
Okay. Overturning. The active soil pressure would also tend to overturn the footing about the toe. So if you had enough pressure here, you can picture that this is trying to push the wall over. And if you had inadequate proportions or mass back here, this wall could literally just roll over about the toe right there and fail. So it would be a stability failure, but it could fail about the toe there. So we need to check that. So about the toe, you have the horizontal lateral pressure, H sub A, times this eccentricity measured from a third of the wall down to the bottom of the footing. The overturning moment is equal to the lateral force H of A times its eccentricity to the toe. Your resistance, the resisting moment, R sub M, is equal to the weight of the stem wall, the soil above the footing, and the footing itself, each times the eccentricity to the toe. So the weight of this giant chunk of soil bearing down on the footing times E to the centroid of that, and you have the weight of the wall times E to the toe, and the weight of the footing times E to the toe. So each one of these gets summed up for the total resisting moment. Building Code Section 1806.1 specifies that the factor of safety for overturning also must be 1.5 when using service loads. Again, ASCE 7 Section 241 specifies that D, L, and H loads all have a factor of 1.0. Live load. You could, and in many times do, have some specified live load up here. So if there is live load above the wall and retained soil, then it can be added to the lateral load as additional lateral pressure equal to an equivalent additional soil equal to the live load divided by the equivalent fluid pressure. So in other words, just to throw a number out there, maybe for this particular soil, the equivalent fluid pressure is 40 pounds a cubic foot. So it's producing pressure the same as a fluid that weighed 40 pounds a cubic foot. If I have a live load up here of, say, 400 pounds a square foot, then that is the same thing as adding 10 more feet of soil above here to calculate your soil pressures. Because 400 divided by gamma EF, 400 over 40 would be 10 feet. So the procedure is, if you have a live load up here, you put more dirt as an equivalency and calculate your soil pressures based on that additional dirt. Does that make sense?
Yes.
Was that an okie dokie, or was that I'm hopelessly
Yes.
lost?
Makes sense.
All right, okay, just checking. If anybody is hopelessly lost, I do hope that you would throw up a flag and let me go back over to help. I don't want to get you too lost. This actually is a project. We just finished like our 4th project of these. We had this exact scenario where we were providing precast as lagging between big, well, we did, all of it was precast. This was like a precast cantilever beam. This was a precast horizontal beam, and we had precast planks in between them taking the soil pressure. And what is up here, and I say is because it's built now, what is up here are 2 railroad tracks that, what do they call that thing? The coaster or the surf liner? One of those guys that goes to San Diego. The rail goes right above this. So we had to take this live load from railroad trains, you know, big commuter trains full of people, and we had to calculate an additional lump of soil as an equivalency and then design the wall for all that extra pressure from the train.
How thick was the wall?
Pretty darn thick.
Yeah.
Yeah, these pieces were like 3 feet deep by 2 feet wide. So this was 3, and in and out of the page was 2. This was like 3.5 by 4, and it went back like 15 feet. This went up like 30 feet, and the pre-stressed planks between them were 12 inches thick. So it was a pretty sturdy system.
Jesus.
So we're pretty happy. It won an award from PCI, is the Precast Concrete Institute. And yeah, we're just kind of toot my horn a little bit, but we won an award for that project. It was pretty cool. For concrete design, the stem wall is designed for bending and shear. The critical section for bending is at the footing wall interface, and a critical section for shear is located at a distance D of the wall section up from the top of the footing. The footing is designed just as we did for strip footings, so it's on a per foot basis. The soil pressure must be evaluated with non-uniform pressure due to overturning moments. Retaining walls are usually designed with the wall portion battered back. That way, when the wall rotates and deflects under lateral loading, the top doesn't look like it's leaning over. And here's what I'm talking about. So the inside face would be vertical, but the outside face is usually and intentionally battered back. So this may be 2 inches or 6 inches, you know, whatever you want to do there. But the reason why we batter this wall, I guess twofold. One is you don't need all of this section width at the top. Your moments and shears are highest at the bottom. So you're tapering the wall as the loads are decreasing. But you also do it because for every load, there's a deflection. And there's just no way that you can put load on this wall and this thing's not going to move out. They always move out. It's just a matter of controlling how far they move out. But if this is a 30-foot high wall, it would not be unusual for this to move out 2 or 3 inches once this is all kind of settled in place. So if you made this vertical and this thing is leaning out 3 inches, people might get a little uppity about that and say, hey, your wall's failing over here. But if this was battered back 6 inches and it deflects out 2 inches, good design, good job. Okay, any questions up till now? Okay, so let's do an example for a shear wall. And I'm going to take some of the guesswork out of the example for you. I'm going to give you all the dimensions of our proposed retaining wall. So again, here's the toe. The footing is going to be 14 inches wide. This retaining wall in and out of the page could be 10 feet deep or it could be 100 feet deep. Doesn't really matter. We're going to design it on a per foot basis. The wall itself is 17.5 feet tall. The footing is 30 inches thick. We're going to set back the wall 3.5 feet from the toe to give us 9 feet of back span here. This is actually kind of known as a counterfort. And so the 9 feet really helps us because it's picking up all the weight of this soil. In other words, for this whole thing to lean over, it has to pick up 9 feet of soil. So that's really kind of holding it down. The wall itself is designed as 18 inches thick at the base and 1 foot thick at the top. Soil parameters. The density of the soil is 110 pounds per cubic foot. The equivalent density of the soil is only 40 pounds per cubic foot. Mu is 0.55. That's the coefficient of friction on the bottom here. Q sub A, my allowable soil pressure is 3,500 PSF. My concrete is 150 pounds a cubic foot. F prime C is 4,000 PSI. And Fy is 60 KSI for the steel. We would like to calculate our active lateral pressure. So P sub A, the pressure PA, is the equivalent density times H. So 40 pounds per cubic foot, plus 17.5, plus the 2.5 of the footing depth, gives me 800 pounds per lineal foot. at the bottom here. 800 pounds times 17.5 plus the 2.5 of the footing gives me, times half for a triangle, gives me 8 kips. And my 8 kips is applied at 17.5 plus the 2.5 over 3. So again, I'm working with a triangular stress pattern. The triangle goes from the top of the wall to the bottom of the footing for overall push against the footing. And so my eccentricity is 6'8" from the bottom of the footing. So I have an 8 kip load applied at 6'8" from the bottom of the footing. Therefore, my overturning moment is 8 kips times 6.67 feet is 53.4 kip feet about the toe. So to find my resisting moment, I have to calculate each one of these 4 components. Component number 1 is the footing itself. So I have 150 pounds a cubic foot times 2.5 feet thick times 14 feet long times a 1 foot out of the page gives me a total of 5.25 kips in weight. P2 is 150 pounds cubic foot. P2 is the triangular portion of the wall here. So it's 17.5 feet tall times half for a triangle times 0.5 is the 6 inches of the base, 1 foot out of the page, is only 660 pounds or 0.66 kips. P3 is the balance of the wall, 17.5 feet tall, 1 foot wide, 1 foot deep, 2.63 kips. And P4 is the density of the soil times 17.5 feet tall times 9 feet wide, gives me 17.33 kips. You can see where the most of my resistance is coming from this backfill. So P total is, add these together, you get 25.9 kips. And now we have to calculate what our moment arm is, because each one of these components has a separate eccentricity. So the eccentricity of the footing is the 14/2 is 7 feet from the toe. E2 is 3.5 feet plus 2/3 of the 6 inches here. That's 3.83 feet. E3 is 3.5 feet plus half 6 inches plus the 1 foot width of the wall over 2, 4.5 feet. And E4 is 3.5 plus 6 inches plus 12 inches plus the 9 foot backspan over 2, and that gives me 9.5 feet. Therefore, my resisting moment part 1, 5.25 times 7, 36.8. The battered part, 0.66 times 3.83, 2.5. 2.63 kips for the rectangular portion of the wall times 4.5 feet is 11.8. And 17.33 kips times the 9.5 eccentricity is 164.6 kip feet. Sum it all together, I have 215.7 kip feet. My factor of safety then is 215.7 over my demand on the previous slide was 53.4. I have 4.04 as a factor of safety, greater than 1.5, so we are okay for overturning. Any questions there? Okay. Calculate our sliding resistance. The axial load of the whole assembly, as we just calculated, is 25.9 kips. So my resisting force is, now I changed my mu to a P. That's supposed to be, actually M was mu. So mu times P is 0.55 times 25.9. My resisting force is 14.2 kips. My factor of safety is 25.9 What? I did it again. Another typo. Okay, multiple typos. This is unacceptable. Mouse. Okay, this was mu symbol, mu, insert, close, P 14.2. So this is 14.2 divided by 8 is 1.78. There we go. Sorry, guys, couldn't let that one live. Okay, so this is correct, and then now it's all wrong again because the slide keeps repeating. But anyway, I fixed it on that one. So mu times P, 0.55, 25.9 is the total vertical weight. It's 14.2. The horizontal force we found was 8 kips, so 1.78 is greater than 1.5. We're still okay. Any questions about this before I hit this button and they all turn back to the original numbers? Okay. So they all turned back to the original numbers. Okay, so now we have checked overturning, we have checked sliding. Now what we need to check is allowable soil pressure. For the purposes of soil pressure, eccentricity is measured from the center of the footing. Everybody remembers P over A plus or minus my over I, the flexural formula for mechanics. Well, that my over I, y is measured from the center and I is calculated from the center. So we need to take everything from the center of the footing. So we need to reevaluate what our eccentricity E is. E for 1, the center of the footing is the center of the footing, so that's 0. E2 is, this is 14, so this is, half of this is 7, minus 3.83 is 3.17. E3, 7 minus 4.5 is 2.5, and 7 minus 9.5 is minus 2.5 here. So now I have all my eccentricities about the center of the footing. My moment for part 1 is 0. For part 2 is 0.66 times 317 is 2.1 kip feet. For the rectangular portion of the wall, it is 2.63 times 2.5 is 6.6. And the soil at 17.3 times minus 2.5 is minus 43.3. So the total overturning moment, including H of A, is 53.4 from H pushing against this. We calculated that for overturning, plus the 2.1, plus the 6.6, minus the 43.3, gives me 18.8 kip feet. That is my resultant moment about the center of the footing, 18.8. So, as I just said, bearing pressure is P over A plus or minus my over I, but we're looking for the maximum, so that's going to be plus. P is 25.9, A is 14. 14 times 1 is 14 square feet. Y is 14 over 2, or 7 feet. I is BH cubed over 12. 1 times 14 to the third over 12 is 228.7 feet to the fourth. So Q is P over A plus my over I, 25.9 over 14 plus 18.8 times 7 over 28.7 gives me 2.425 KSF, less than 3.5, so we are okay. Okay, any questions up to this point? So we are on slide 154. And I think this is a good break point because what we just covered were all the soil parameters and all the soil checks required by code for our retaining wall. So in other words, if this retaining wall, let me get back to an illustration. Here we are. So if the retaining wall and the footing is all assumed to be a solid, rigid body that will not break or deform, then we've done all our checks that this whole thing as a solid body will not press into the soil too much, will not slide against the soil too much, and will not overturn in the soil. So what we'll pick it up next time is now that we have the stability under control, now what we're going to do is factor our loads, find a factored soil pressure down here and here against the lateral side, and design all of the concrete elements for shear and flexure so that we know the wall itself is sufficiently strong to resist those soil loads. So we'll pick it up next time with that. We do have a few minutes left. I just want to open it up. If anybody would like to, I'll just open it up. If anybody had any other questions on their homework or any questions that they would like to ask about the final now, we certainly will spend more time on that on Thursday. But I'll just open up the floor. It's your time if you'd like to ask any more questions.
Professor.
Yes.
So we did not have any homework on when we looked at structural systems. That was lecture 12. We don't have any homework on that. Is that still fair game to be on the 9 now?
I'm sorry. It was lecture 12 was on structural what?
It was structural systems, like we had a column and then we had the beam on top. And then we were trying to see if it's a braced frame or not.
Oh.
Yeah.
Okay. Okay. Let me put it this way. The concepts are open to the final. The concept. What is a brace frame? What is a sway frame? How do you find psi A or psi B using that chart? Those concepts, we spend a lot of time on them in lecture, so those concepts are definitely open to the final, but I will not ask you a question that is going to make you design a column that's a sway column or a non-sway column and calculate the slenderness, and there's just no way I can do that, a whole problem. That's why I didn't give it to you as a homework. It was really too much even as a homework problem. But it is fair game to say that I could ask you one part of something like, what is Euler's buckling load for, and I give you all the parameters. Does that make sense?
Yeah, that makes sense.
Okay,
That
so
makes sense, yeah.
I would encourage you to review that lecture, read that section in the book, and be familiar with it, but I cannot ask you to do a full-blown problem like I did in the lecture. You saw how long it took to get through it just in the lecture.
Yeah. But does that also go with the concept of when we're designing columns? First, like we have to find the 5 points and stuff. Those take a long time too. Like in the homework, we only found 1 point.
Correct.
So is that like something to look forward to, or is it? Because like I was thinking, like when I'm reviewing right now, I'm just like, how can I do this faster? It's not like how can I learn it. It's more of how can I do this faster.
Well, that's really kind of a loaded question now, isn't it? The point of the final is for me the test that you have grasped and understand these concepts. And it's my job to try to do it in a way that is achievable in 2 hours with being absolutely unreasonable with the time constraint. So I'm going to ask questions that I feel test your concept and your understanding of the material, but I'm going to ask questions in a way that can be reasonably completed in 2 hours.
Okay,
So
so
in other words, I'm not going to tell you don't worry about this or don't worry about that. That's not going to be on the final, but I'm going to kind of give you guidance on to, there's no way I'm going to give you find the interaction diagram for such and such column that takes 3 hours, and that would be the only problem on the whole final.
yeah,
So
that was my question. Like,
yeah, so I
yeah.
have to do it in a way that can be achievable in 2 hours, and I don't want to spend all your time on one problem. I want to capture some breadth of this course. So I by necessity are going to have to simplify some of these things, but you still should review all of the material because you never know when I simplify it, what I have simplified it to.
Makes sense. Makes sense.
Okay, and then I had a private question that read, Professor, the retaining walls won't be on the final, right? That is correct. The retaining walls will not be on the final because this is the last lecture and we haven't done any homework on it at all. So yes, you are safe to assume that the retaining walls will not be on the final. But footings are wide open. The stuff that we just finished today, one-way shear, two-way shear, flexural, soil pressure, all of that most definitely is within the scope of the final. Okay, would anybody else like to ask a question at this time? For the homework due today, can you specify if the footing is a strip footing or a spread footing? Oh, homework 8, that's a square. It says square on it, homework for homework number 8. That's a square footing, so that's a spread footing. No problem, no problem at all. Still got 7 minutes. Anybody who's been shy for the last 10 weeks, I'd love to hear your voice.
Professor, I think you answered this question already, but if AS min is greater than AS required, we go AS min?
Yes, of course. That applies to what we did at the beginning of this course when we designed beams. And you had the steel required for flexure, but you have to check that against AS min. If AS min is greater than the steel required for flexure, then you have to provide at least as much as AS min. We did that for shear design, where you find the steel required for your loading for shear, and that would dictate a certain spacing. But there's also a minimum amount of shear steel that you have to provide, which might dictate a larger or smaller spacing. Whichever produces the smallest spacing, that's what you have to provide. And then we just did footings where, again, you had minimum steel for temperature and shrinkage, and you had minimum steel for flexure. Whichever one is the greatest demand, you have to satisfy that with your steel design.
Got it. Thanks.
Professor?
Yes.
Okay, is it possible to go over some problems that you think it's important for us to know on Thursday, like example problems, whatever you think it's important?
I don't want to do that because I don't want to be accused of teaching to the exam. You know what I mean? That I can't do that because I mean that would be basically like, all right, everybody, the test is on everything I've talked about for the last 18 lectures. So why don't we do this problem now that's going to be exactly like something on the test? You can see my position. We don't want to do that. The final needs to be something that comprehensively tests your understanding of the whole concept of reinforced concrete. And I'm going to do that with 4 different problems that I have randomly and arbitrarily selected that would test the breadth of your understanding. So now if you want to bring a problem to the Thursday and we have time to go over it, you bring me a problem, say, I am utterly and absolutely confused about this. Could you help me? Well, sure, of course, we can go over that.
Okay, thank you.
Anybody else would like to ask a question? Alrighty then, going once, going twice. Okay, again, I apologize that we have to do this virtually. I really do. I really feel like we did the best we could, and hopefully each one of you feels the same. I hope that we did the best we could. But I would love to see all of you, except for those who are graduating and never want to come back, but I would love to see all of you back in a classroom where I can see you and I can see your faces, and there's just no substitution for looking around and just seeing, you know, people nodding and people saying, yeah, I got this, quit spending time on this, or people looking at me with that deer in the headlights look and like, I don't even know what to ask. I'm so lost. There's no replacing that, but hopefully we've done the best we could. If anybody thinks of questions between now and Thursday, we have an office hour on Thursday as well. I would love to see some first-time callers come in, ask your questions. If not, bring whatever you like to Thursday. I think the lecture that we have left over for Thursday will take 30 to 45 minutes maybe. And after that, it's going to be completely your time to ask whatever you would like to ask. So if you think of anything between now and then, please bring it to our lecture. And other than that, I wish you all a good evening, and we will see you on Thursday.
See you, Professor.
Thanks,
Thanks.
Professor.
Thank you.
Have a good one, Professor.
Thank you. You too.
Well, Professor, sorry.
Yes.
I just remembered. I'm gonna have to email you my homework 8. You recall me telling you that issue I had about Blackboard?
I do.
I'll get that into you before midnight, of course, on time, and then for record.
Yeah, that's totally fine. Just email it to me before the night's over, and I'll remember to grade it from there.
I appreciate it. Sorry for the accident there.
No problem. It happens.
Alrighty. See ya.
Okay. See ya. Good night.